Well, hello, everyone. I'm John Shenot with the Regulatory Assistance Project, and I'd like to welcome you to today's webinar on the role of energy efficiency in a decarbonized economy. I'll be your moderator today, and I'm looking forward to some interesting presentations from three of the most thoughtful leaders this country has on energy policy and regulation, in my opinion. Each will offer a different perspective on this hot topic. But because we want to make this time as valuable as possible for all of you, our audience, we're going to keep the presentations brief, and we're going to reserve a big block of time to field your questions. Before we get started in earnest, let me explain just a couple of logistical details. Because there's a large number of people attending today's webinar, we're going to keep all of your phone lines muted. However, you can submit questions at any time during the webinar by typing them into the questions box on your GoToWebinar window, which is shown here. After we've heard from all three of today's presenters, we'll do our best to get to as many of your questions as we can in the time available. Now, today's webinar is scheduled to run for 60 minutes, but the presenters and I are going to stay on the line for an additional half hour if there are more questions to be answered. Those of you who need to leave at the end of the hour can do so. Those of you that wish to stay, we'll be here to answer more questions. And finally, you should also know this webinar is being recorded, and in a few days we'll send all of you a link to the recording and to the slides. So earlier this year, RAP was invited by the publishers of the Electricity Journal to guest edit a special issue on a theme of our choosing. We were, of course, honored and really excited to have this opportunity. And the theme we chose to focus on was energy optimization. The title and the entire premise of the special issue is that energy optimization is the key to affordable, reliable decarbonization. The special issue features 9 articles by authors from RAP and from other organizations, each addressing a different aspect of the energy optimization challenge. I've included a link here to the special issue, but please note that a subscription to the journal is required to download or read the articles online from that link. However, for the remainder of today, and today only, unfortunately, you can download copies of all the articles in the special issue for free if you go to the blog I wrote about the special issue and follow the links embedded in my article. The link to the blog is there on your screen. If you don't have a subscription to the Electricity Journal, I strongly encourage you to go to this blog post and download articles today. If you wait until tomorrow, free access will no longer be available. And we will show you this link again later in the webinar, and we'll leave it up on the screen for a while so you can jot it down. So, what is energy optimization anyway? Well, to be honest, I'm not sure if the staff at RAP have reached consensus on this question. But my own working definition is that energy optimization means making our consumption of energy as efficient and as flexible as possible in order to take maximum advantage of renewable energy when and where it is available. If we don't do this, we could probably still get most of the way toward a decarbonized economy, but we would have to build and pay for vastly greater quantities of renewable generating capacity and energy storage, or we'd have to accept a less reliable power system than we enjoy today. Energy optimization offers a better way forward. Fundamentally, it requires some new thinking about, I'll say, the intersection between energy efficiency and economic efficiency. I think to optimize our use of energy, we have to stop compartmentalizing our energy efficiency efforts with separate policies and separate programs for electric utilities and for gas utilities and for transportation fuels. We also need to minimize curtailments of renewable generators. Curtailments are a form of energy waste. And we have to minimize those curtailments by making more of our energy consuming devices flexible and shifting their consumption to utilize any excess wind or solar power. So in short, I see energy optimization as combining the next generation of energy efficiency and demand response techniques into one coherent package that keeps the lights on with clean energy at the lowest possible cost. For today's webinar, we've invited 3 of the authors of articles in the special issue to briefly share their key takeaways about the future of energy efficiency and demand response and why they think this topic is important. After all 3 have presented, then we'll take your questions. We'll hear first from Steve Nadel. Steve is the Executive Director of the American Council for an Energy Efficient Economy, or ACEEE. Next up will be Sue Coakley. Sue's the Executive Director of Northeast Energy Efficiency Partnerships, or NEEP. And last but not least will be Carmen Best. Carmen's the Director of Policy and Emerging Markets at a company called Recurve. So let's get this show started. Steve, the floor is yours. We're looking forward to your presentation. Steve, you are muted.
Sorry, thank you. Hi, thank you, John, and I look forward to all your questions. I'm going to summarize my article, which is on proven energy efficiency policies and how they can evolve to address future needs. In the paper, we had a set of graphs that we've just updated in our study halfway there, showing how energy efficiency can reduce U.S. energy use and greenhouse gas emissions by about 50% by 2050. It's going to take many different measures, as this rainbow chart shows. But I'll start going to some of the policies and measures that will do that. So, policies. This chart shows the savings from some of the major energy saving policies in 2017, so capturing the impacts from over the preceding couple of decades. As you can see, vehicle fuel economy standards have been the largest, followed by appliance and equipment efficiency standards, etc. But I'll be talking about each of these in the next few minutes, including how they can evolve going forward. Starting with fuel economy standards. This chart shows fuel economy progress since the late 1970s. As you could see, we made some progress in the 70s, early 80s as CAFE standards, corporate average fuel economy standards, were improved, and we had a long level period where the standards didn't change. But in recent years, the standards have gone up quite a bit, and fuel economy has gone up as well. The dotted lines through 2018, 2019 are in effect and have gone up. The Trump administration is proposing to significantly slow the increase starting in 2022, and we will see what happens. They're pretty sure they're going to propose that, but it will ultimately be up to the courts to decide whether what they're doing is kosher or not. But in addition to the federal fuel economy standards, California has zero emission vehicle requirements that require a certain percentage of vehicles be electric or fuel cell or hybrid. A dozen other states have also adopted those California standards. California is going to be reviewing its greenhouse gas standards for both light duty and heavy duty vehicles in the next year or two. And so that will affect not only California, but could well be the template for future federal action when we get to a next administration. It's clear the Trump administration is not interested. And then perhaps we might want to consider a national zero emission vehicle standard to complement the CAFE standard that will help push some of these advanced vehicles, electric and fuel cell, into the market while the fuel economy standards continue to make sure that the conventional vehicles continue to improve. So the next major policy is appliance equipment standards. In this chart, you can see at the middle line, which shows what energy use has been and is projected to be with the standards in place. The line above that shows what energy use would have been if we didn't have the standard. This is national energy use. And the dotted line at the bottom looks at additional savings from setting new standards beyond current products. I would note that the Energy Star is an important complement to standards, that it can save significant energy beyond the standards by encouraging best-in-class products. It also gets the market, the manufacturers, the retailers, et cetera, used to the higher efficiency levels and helps lay a foundation for potential future upgrades to standards. So going forward, there are a lot of opportunities to update the existing standards, maybe add a few products, such as electric vehicle chargers is one example people suggested. When we add products, it could happen at the federal level or the state level. And this past year, 4 states passed new state efficiency standards because at the moment the federal government is not interested in adding standards. I would also note, to lay the groundwork for one of the future speakers, there may be opportunities to add a requirement that equipment be connected as part of these standards so that it not only saves energy, but could be more dispatchable as part of demand response programs. So of the savings from standards going forward, about 70% is from about a dozen products, whether it's water heating, heating and cooling equipment, shower heads, faucets, traditional appliances, or some industrial equipment. These types of equipment really have a disproportionate impact and should be priorities for the standards program, but also for voluntary efforts to promote this higher efficiency equipment to lay the ground for future standards. Next, we have utility programs. They've been another major source of energy efficiency savings. The upper graph shows spending on these programs, both by the electric utilities in blue and the gas utilities in orange, but then savings on these programs down below. The blue is the incremental savings each year from measures installed that year, whereas the red is the savings in a given year, counting all the measures installed in previous years. And since the blue has gone up in recent years, the red is also climbing much more substantially. This is one of the key areas for state and utility action to favor energy efficiency. There's a lot that can be done to update the programs and move them forward to the next decade. This shows some of the big opportunities going forward. We've gotten a lot of savings from lighting. That's great. There will still be some lighting savings, particularly in the commercial industrial sectors, but we need to diversify our utility sector programs, whether it's smart buildings, lighting controls, providing feedback to consumers in real time so they can react to it, strategic energy management, zero energy buildings, more efficient equipment such as heat pump water heaters and commercial and residential air conditioners, industrial equipment, plug-in loads. All of these things are going to be very important as we move forward through the 2020s to continue the savings from utility efficiency programs. Another important area is building codes. This graph shows progress in building codes since 1980, where the 1980 code is equivalent to 100. And you can see how in the case of commercial shown by blue, the current codes are probably about 50% lower energy use. For residential, it's about 40% lower energy use. But this one shows the dotted line showing that many groups, including some of the code bodies, are trying to target getting to zero energy codes by 2030. Zero energy, sometimes they're looking at zero carbon. To make progress on this, we have to make steady progress each of the code cycles, but a lot more needs to be done on voluntary programs to promote zero energy and zero carbon buildings so that the market is very familiar with them, and when eventually we get to the point of trying to talk about codes that require those levels of performance, that the market is ready for that. I'd also note that code implementation and compliance is very important, and spreading codes to additional states. Roughly speaking, about 35 of the states now have a reasonably up-to-date code. Those without a reasonably up-to-date code should update them or establish codes, and obviously those with codes should continue to update them as we move, hopefully, down this pathway. So those are some of the more proven technologies or proven policies that we've been using for several decades. We're going to need to complement those with additional approaches. Building benchmarking and retrofit policies are very important. We're up to about 20 cities now that require commercial building benchmarking, and several cities are requiring commercial buildings to meet performance standards, effective typically about 5 years from now. Strategic energy management for industrial, large commercial and institutional customers, where every year it's a continuous improvement process, and every year you ask, what are we going to do this year, as opposed to decide if you're going to do anything at all. Smart building, smart manufacturing, we see as some of the biggest opportunities out there. And then let's not forget the efficiency of airplanes, freight, and people movement, because transportation is now our largest greenhouse gas emitting sector, and we need to do more there. So to conclude, the traditional energy efficiency policies have saved much energy. They can continue to be a major source of energy savings and emissions reductions, although some refinements would be useful. And then additional complementary policies, as I just talked about, will also be needed. But with that, I look forward to the other presentations and to responding to your questions.
Great, thanks, Steve. Next, we are going to hear from Sue Coakley with a different perspective on the future of energy efficiency. Sue?
Great. Thank you, John, and good afternoon, everyone. I'm thrilled to have this opportunity to talk with you all. My comments today from the Electricity Journal article on energy optimization is 5 strategies to transform our buildings for a low carbon era. The key ingredient in all of these is energy efficiency. Let me just begin to say a couple things about NEEP that will help you understand some of the comments I'll make here in our strategies. We assist Northeast states from Maine to the District of Columbia to accelerate efficiency as a least cost resource. We've been doing that for about 25 years. In recent years, we've turned our attention to efficiency, including heating electrification as a resource to meet not only reliability goals, but carbon emission reduction goals. With that, we conducted in 2017, next slide, a regional opportunity assessment for strategic electrification. And we found there that switching to advanced heat pumps for space and water heating in place of burning fossil fuels is a major opportunity to reduce energy use and carbon emissions. To maximize the economic and reliability benefits of this strategic electrification, as we called it, we identified 3 elements. These are similar to some of the things John Shenot said earlier about efficiency and flexibility and energy optimization. So the first is in building decarbonization, high performance heat pump technology for space and water heating that works effectively under a wide range of climatic conditions. Secondly is to improve the thermal performance of buildings, insulation windows that retain conditioned air for a longer period of time. This reduces the size of heat pumps and enables homes to serve as a flexible grid resource during peak periods. The third element are smart controls, rate designs, and programs that engage efficient homes and buildings to respond to grid signals to meet peak demand. This is something that Carmen will be speaking more about in her comments. But these 3 elements are important to grid reliability, energy affordability, and total carbon emission reduction. Next slide. Something that has been really useful to us to understand what the impacts of this efficient electrification and decarbonization can be has been this analysis about the change in total building energy use when we use heat pumps in place of fossil heating. Buildings are a major contributor to carbon emissions around the country, ranging from 25 to 50% of carbon emissions in the Northeast region. Our region, it's about 35% of total carbon emissions. So we can't get to climate stabilization unless we deal with our buildings. So this graph shows the broad adoption of advanced heat pumps for space and water heating in homes and buildings across New England, New York. And it shows that by having a turnover of our heating equipment over time to be heat pumps in place of fossil heating, we can reduce our total energy building needs building energy needs by 2/3 from current use. That's quite remarkable. It's a very large efficiency gain. And that's why we think of electrification of space and water heating as a deep efficiency. What you'll see here, the left axis is trillion BTU of energy for building consumption. The right axis is market share of heat pumps each year going to 2050. And as we go up the market adoption curve for heat pumps as a primary heating system during replacing during natural cycles of market activity, getting to 100% by 2045, we can see the huge reduction in total energy requirements. We also see on the gray curve the reduction in fossil fuels for heating. We see an increase in the green curve of electricity use, but overall we reduce our total energy requirements by quite a lot, by 2/3. Next slide. When we try to assess what does this mean for carbon emissions, we find that when we look at buildings' energy use, when we broadly adopt heat pumps, as we showed in the prior slide, the blue curve shows you that we significantly reduce our greenhouse gas or carbon emissions from buildings by switching to heat pumps. This is before we even modeled in the effect of thermal efficiency improvements. This gives us great hope that building decarbonization can really make a big difference and help us drive us towards climate stabilization goals. Next slide. So I'm going to, my last slide here is just about 5 strategies that can help us accelerate building decarbonization and maximize the economic and reliability benefits. In our paper, we present five approaches. The first one is buildings as batteries. Again, John mentioned a bit about this. Adding electric load for space and water heating can reduce electric rates if we use existing T&D systems. We increase the capacity factor, that can have a rate reduction effect. However, if electrification adds to system peak, say during a long cold spell, that can increase system costs. So treating buildings as batteries through thermal energy or energy storage enables buildings to respond to grid signals and to minimize energy requirements at peak. This can be very important to maintaining reliability, affordability. So Carmen will speak more about this in her comments. Secondly, we are in an early stage of market adoption of heat pumps, and therefore the costs and the equipment options are, costs are high, equipment options are limited, and we need to drive it to scale. So driving scale will increase competition, increase options, as well as reduce costs of installation. And so currently we actually see programs across the country offering incentives for heat pumps for both cooling and heating. In the Northeast, 7 states now offer incentives for heat pumps for efficient heating. Thirdly, is the need to work within natural market cycles. So the curve that I showed earlier about market adoption assumes that heat pumps will be installed at the time of new construction, renovation, rehab, equipment replacement, those natural cycles when people are making investments in their buildings and in their equipment. When we make an investment in decarbonization strategies, thermal efficiency or heat pumps, at those times, it's the incremental cost versus the whole cost of the system replacement. This is more feasible for us as well as more economic in terms of adoption. Our fourth strategy in this early cycle is to focus on high value markets. The best economics for these early markets, here's a few examples that we had in our paper. In the Northeast, we have a high use of oil and propane in our homes. In fact, the large majority of heating oil is used in New England and New York in the country. That is a more expensive fuel, oil and propane, and the economics of replacing the use of propane and oil is compelling compared to the cost of putting in a heat pump and using electricity. So that is a near-term market, and we have a number of policies and programs that are leveraging that. A second strategy in terms of high-value markets is really for warmer climates. So heat pumps provide both efficient heating and cooling. In warmer climates, when either an air conditioning system or a heating system needs to be replaced, a heat pump can replace two systems with one, and the economics of that can also be very compelling. A third area, high value market, is areas with fuel availability issues or T&D constraints. Particularly we see in areas of development where there's a requirement for more gas in particular, or just more gas is being used, electrification and efficiency can both reduce the requirements for those constraints. A fourth one of our high value markets is really in the area of affordable housing and community development. We have a housing crisis, affordable housing crisis across this country. There's a lot of effort and investment being made to increase affordable housing, both new and rehabbing of existing buildings. Electrification at that time, along with thermal efficiency, can provide multiple benefits and be very cost effective within those cycles of investment. Finally, the last strategy is working with local government, including affordable housing leaders. Some of the most aggressive strategies in greenhouse gas reduction are being developed and implemented at the city level. For example, New York City, the District of Columbia, Burlington, Vermont. And when it comes to building decarbonizations, cities have the ability to innovate in program design to accelerate voluntary local and regional action. For example, we have seen recent adoption of building energy performance standards for existing buildings in the District of Columbia and New York. Other cities and communities are adopting 100% renewable energy requirements, and those electrification decarbonization policies can be good strategies in that case as well, and provide market momentum for these strategies. With that, I will conclude remarks. Oh, I will just note, sorry, our last slide is for more information, you can go to our website and access resources there, or contact the co-author of this paper, Dave Hewitt, and also myself or Dave Liss, who is our Director of Technology and Market Solutions. Thank you.
Thanks, Sue. Our last panelist is Carmen Best. Carmen, you have the floor.
Thanks, John. Thanks for the invitation to contribute to this series in the Electricity Journal, and of course to share some highlights today. The main premise of our paper is really about identifying new solutions to adapt to the changing grid. New load management and load shaping is happening around the world, even if the local shapes and the animals we may have to deal with vary. Decarbonization and grid optimization are increasingly the common goal, and meeting these goals is significantly enabled through the use of advanced metering infrastructure, which really allows us to understand the marginal value of changes in consumption at a given time and location, and take advantage of demand flexibility as a key path for integration with the grid that really can't be achieved with traditional energy efficiency and demand response alone. So it's really this time value of efficiency or demand flexibility that's going to unlock the grid of the future. Let's dig into that a little bit more. So when you look at the time value of savings compared to the avoided cost, as we're doing in this graphic, it's pretty clear that each kilowatt hour is not created equal. In this illustration, taking the top graph, you can see that the residential program delivering HVAC and shell measures can deliver almost 60% more greenhouse gas emissions reductions per megawatt hour than the commercial lighting program, as illustrated in the second graph. On the left-hand side, you can see the average time value for these programs, and the seasonal variation is shown on the right-hand side of the graphic. So most efficiency programs are only looking at the time value through the lens of a measure-based average load shape rolled into a cost-effectiveness test. And as a result, the significant seasonal time value of this residential program, for example, is lost using this type of test. So the dramatically higher cost-effectiveness score that you can see on the bottom for the commercial lighting program would suggest that it should be the primary investment and perhaps the sole investment, and whole home retrofits are not cost effective. By using the total resource cost test as this signal rather than a stronger time valued signal, one would likely reduce or eliminate investment in improving the demand flexibility offered through upgrades to these homes, and potentially also bypass the flexibility potential of commercial buildings that may only get a lighting retrofit to meet short-term savings goals. This inequality in kWh value, however, does not have to be a burden. It, in fact, can be a significant opportunity by using that time value as a price signal to channel market-based solutions to deliver demand flexibility when and where we need these savings most. To do that, we need to create market structures in which third-party providers or aggregators can innovate, and that starts with a common understanding of performance through standardized weights and measures. Caltrack is a standardized detailed method for calculating changes in consumption due to interventions at the meter. It includes an hourly approach and is being used for meter-based pay for performance currently happening across the country. The hourly methods in Caltrack are an adaptation of the Lawrence Berkeley National Lab time of week and temperature model, and the methods are operationalized in the OpenEE meter, which is an open source code base allowing for transparent, repeatable calculations at scale. And both of these tools are available without restriction to anyone in the market. These projects are maintained through a collaborative community of implementers, analysts, utilities, and other software vendors via the Linux Foundation's focused effort on energy called LFE. So using standard weights and measures tied directly to the grid value of the interventions allows us to build this bridge between demand-side management, our customers or the customers, and the grid needs by sending the right price signals for when and where those resources are needed most. Market actors can then design programs and respond to procurements that capture that value with customers at the lowest cost. With consistent weights and measures and clear price signals, we can enable business models in the market to optimize the value through innovation and creativity. Policymakers, regulators, load-serving entities, and aggregators can all have greater confidence through meter-based accountability. And the data-driven performance feedback loop allows for continued scale or potentially course correction in investments as they successfully deliver or may need to be adapted on the promises to capture avoided costs and the carbon reductions to meet our lofty goals. Let's look at an example that's in practice today. Pacific Gas and Electric is currently running a residential hourly pay-for-performance program where 4 very different program types, HVAC retrofits to energy coaching, all were bid into a very open procurement model that was hosted by the utility. This procurement is you can move to the next slide. This procurement is really the equivalent of a savings purchase agreement where all the aggregators are paid for the savings delivered over time. Aggregators are also eligible for a payment that is 3 times the base kWh payment rate if they can demonstrate that the savings are coincident with summer peak needs from 4 to 9 p.m., which is the steepest ramp on the neck of the duck in their service territory. The program models, therefore, have the flexibility to understand and meet customer needs, and the administrators or the load-serving entity has the consistency and confidence that the savings are real for the grid via the OpenEE meter results. This example of a meter-based pay-for-performance procurement represents a scalable model that considers the full suite of market interactions that are needed to scale demand flexibility with confidence. From the load-serving entity and those that oversee their work to financiers and insurance providers, all the way down to the contractors who are trying to meet customers where they're at with a wide suite of products and services that those customers want and need. So meter-based pay for performance really enables us to finance efficiency more like other grid infrastructure. Let me explain that a little bit. When you finance a power plant or a power purchase agreement, the loan and the repayment is based on the value of the cash flow created by the generation and sale of energy over time. This is called project or infrastructure finance. And pay for performance procurements based on the value of the grid benefit calculated with the open EE meter, for example, helps create a project finance investment for demand flexibility that enables us to finance the efficiency and other value using the same form of finance we employ for other grid infrastructure by creating that same sort of cash flow, rather than relying on a large ratepayer surcharge to cover the costs and balance it through a cost effectiveness test. This model also opens up a streamlined way to sell flexibility straight to wholesale markets. When we finance flexibility as a resource, it enables us to invite outside investors to join us in supporting all the resources that are needed to enable a clean energy future. Thanks for the opportunity to share today, and I look forward to the questions.
Great, thank you, Carmen. All right, we're going to use almost all of our remaining time to answer your questions. As a reminder, because there are so many of you on the webinar, we're going to keep all of you muted, but you can submit your questions in the questions box on the GoToWebinar screen. I have also copied the link here to where you can download free copies of the special issue articles today. Again, what you need to do is go to the link that just appeared on your screen, which is to a blog post that I wrote. Within that blog post, I summarize all of the articles, and there's a link for each article embedded in the text of the blog post. So if you click on those links, you'll get special time-limited access to a free download of that article. If you wait till tomorrow, you'll have to have a subscription. So what we're going to do is we're going to leave that link on the screen while we field your questions, and that way you can have a little bit of time to jot it down. So we have had a number of questions roll in, and I'm going to tee them up and invite our panelists to address the questions. And I want to start with kind of a big important one and invite each of you actually can give your take on this question. And I'll be paraphrasing the questions as they come in, but someone has asked or has made the point that they sometimes hear that energy efficiency is not as relevant as it used to be. As long as everything is powered by renewables, then we're going to decarbonize. So what would you tell an elected official or regulator about why energy efficiency is still relevant and important? And I think I'll let Steve go first.
Okay, yes, I guess I would perhaps reply, yes, it is not important if you don't care about cost or care about reliability, but presuming that you do, energy efficiency can dramatically reduce the cost of moving to an all renewable grid. If we cut the energy use in half, roughly speaking, we're cutting the amount of renewables we need in half, and generally efficiency is lower cost. Also, efficiency and demand response give you a lot of opportunities to better manage the grid. In particular, with an all renewables future, getting from 80% to 100% renewables can be quite expensive, lots of storage, etc. The more efficiency we do, the more demand response we have, we can help manage those costs, as well as manage reliability as well, because those are going to be the times when we're most likely to run into reliability problems.
Sue or Carmen, do you want to add anything to that?
This is Sue, and I'll just, I agree, of course, with what Steve is saying. I'll add a time dimension to that. It will take time to build a renewable powered grid. A lot of the goals are to 2050. In the meantime, it is urgent to reduce carbon emissions, and energy efficiency is something we can do right now, and we can do it at scale, as you saw in my slides showing electrification and efficiency reducing carbon emissions well on our way to the goal, the climate stabilization goal by 2030. So the bottom line is we can't get to where we need to in time unless we do efficiency. We can't just rely on renewables.
I'll play on that same time dimension. I think we also need it to stay there. Once we do build out, and even if we meet 2050 goals, efficiency in some respects is a renewable resource. We've seen improvements in technical efficiency over time. A recent report from IEA suggests that we've slipped a bit on that front. But it's really important to maintain competitiveness, to continue to improve technical efficiencies, and for the same reasons that Steve and Sue are pointing out, for cost purposes, and just to enable continued growth and prosperity across the globe.
Great. Let's take another question. I think I'm going to send this one to you, Steve. How can efficiency investments be implemented in a way that is equitable and that focuses on the most vulnerable populations first?
Okay. I mean, we're going to need reductions for everybody, but yes, we need to make sure that the most vulnerable populations in particular get at least their fair share, if not more. A couple of things. By focusing on the typically homes that are the leakiest, the biggest energy wasters, often they have better economics than homes that are moderately inefficient. So that would be one, really go after those high users. I know there's some programs in the Southeast where they've just been going after these SIVs and coming with some very cost-effective savings. Another thing is a number of states actually have set aside to say, yes, we need to make sure a certain portion of our budgets, a certain portion of our savings are for low, moderate income families and communities. So that would be something else to do to really make sure that those who most need these services will get them.
Thanks. Here's one for you, Sue. I think this is up your alley. So do natural gas fueled combined heat and power systems have a role to play in a decarbonized economy?
Oh, thanks, John. Yeah, well, they do. The reality is that our transition to not burning natural gas the way that we are today, quite clearly we can't achieve our climate stabilization goals using burning gas in the way that we are. So we have to transition away from it. In the meantime, we need to think about what are the highest and best uses of gas as a bridge to this future where we are carbon free or carbon neutral. And CHP is a very high efficiently way of using gas. So there'll be some applications, whether they're industrial or institutional, where that will continue to be an important use for a while as we transition to the ability to electrify with carbon-free electricity all of our heating.
Yeah. Carmen, someone has asked you to say a little bit more to clarify how AMI and smart meters, advanced metering and smart meters, how they allow us to do smarter evaluation of energy efficiency savings and verification of those savings.
Sure. I think the main thing is that it allows you to have an analysis that has the real data for that time dimension of when and where the savings are happening or when the consumption changes are occurring. Whereas I think with most traditional energy efficiency evaluations, you might be able to do that on a sample basis after the program has been implemented for a handful of buildings with on-site metering and that sort of thing. But when you can have an AMI infrastructure available, you can be doing that for a whole program while it's in progress for all the customers that are participating in that program. as well as all the customers who may not be participating. So you can really use it to help target when and where you might be wanting to have these interventions to improve your cost effectiveness, even if you can't change the calculation metrics that you might be subject to. And also just make sure that understand at first how those interventions are affecting the grid, and then take the next steps to modify program designs and make sure that you're incenting the types of interventions that can shape and shift long-term energy use for those customers.
Thanks. Here's another one for you, Steve. I hope this is up your alley. What about efficiency on the utility side of the meter? Is ATEEE looking at making the grid itself more efficient? And how significant is that relative to what happens on the customer side of the meter?
Okay. Yes, we are looking at what could happen on the utility side, and it is significant, although not nearly as significant as all that could be done on the customer side. But a number of utilities are implementing conservation voltage reduction, where they sense the voltage at the outer ends of the grid and can reduce over voltage as long as the outer edges of the grid are getting adequate power, typically getting 2% or so, maybe even 3% savings, depending obviously on the circuit. Amorphous core transformers is another big saver. I actually had them in one of my slides, but in the interest of time, I didn't go into them. So thanks for raising those. But definitely there are things that can and should be done on the grid. I'd also point out some of these things like the conservation voltage reduction, while it's on the utility, it's out on the utility side of the customer meter, the lower voltage mostly reduces energy use on the customer side of the meter because there's a lot more linear feet of wire in all the homes and businesses, and it will actually reduce their losses.
Okay, thanks. All right, Sue Coakley, how do we address retrofitting affordable or low-income housing with heat pumps or electrifying those buildings when the building's tenants are renters and there's a split incentive issue? Any thoughts there?
A few thoughts. And I've actually seen some good examples of affordable multifamily housing being retrofitted to reduce total costs. So it really means working with both landlords and with tenants and having programs and incentives that encourage both. On the one hand, you have new construction. We have the example in Pennsylvania where their annual solicitation for affordable housing construction for their low-income tax credits, they have a requirement, or not a requirement, but an additional weight for projects that come in that have passive house design. And as a result of that, those affordable housing projects coming in, 75% of them that are selected are passive house design at no additional cost. So right at the get-go, both the landlord and the tenant are getting the benefit. 13 other states have now adopted that model, and we see passive house design moving into new construction for affordable housing. In existing housing and retrofitting it, we have a range of initiatives across the country for preserving existing housing to keep it affordable by improving it. And there are initiatives that involve states and cities to invest in that affordable housing, to update it and make it appropriate, but also to make it efficient for the future. And so it's this time of rehab renovation that makes a difference. Finally, I'd be remiss if I didn't talk about weatherization programs. We have a very big weatherization program that's been working across the country. It's funded in part by DOE, and then states and utilities often augment that funding, and that weatherization program is reaching low-income residents and providing efficiency improvements to houses as well as replacement of heating systems. So that's another venue that where we can serve them.
Thanks, Sue. So Carmen, We got a question here asking you for a clarification.
Mm-hmm.
You pointed out how not knowing or ignoring the timing of energy savings can mask the value of some measures or exaggerate the value of other measures.
Mm-hmm.
Someone has asked if there are any utility commissions or utilities that you know of that have adopted this different view of valuing energy efficiency, a more time-sensitive view of the value of energy efficiency. And
Mm-hmm.
if there aren't, do you have a sense of what it will take to get there?
Two-part question. First of all, I'll come back to my home state, which is California. The legislature actually adopted in 2015 a law that there were two of them that came out at the same time, SB 350 and AB 802. And SB 350 was a law that required doubling of energy efficiency, not just for the utility programs, but statewide. And it also adopted a concept of normalized metered energy consumption, which is a new acronym that we've had to get used to in the state, that really is kind of a first step of going to meter-based quantification of energy efficiency. Now, that hasn't been tied directly yet to the valuation structures. There's still the total resource cost test in California is still the primary test, but that is up for reconsideration. And I think the power and the value of the AMI opportunities to optimize are going to play into that conversation significantly. I would offer another example too for states that have taken on the valuation question. The valuation of DER, the VEDR process that came out of New York in the REV, Reforming Energy Vision processes, I think takes a holistic view for valuation that includes all DERs. And I think that too hasn't tackled energy efficiency time value specifically yet because they're still rolling out AMI in a good chunk of New York, but I think it could. So on the second part of the question, I think what it's going to take is kind of a push-pull sort of approach, wherein the push could come from the vendors, utilities, evaluators, software providers like Recurve, demonstrating the power and the value of AMI and meter-based efficiency to drive this optimization, as well as let's see, I said a push. Which one would be the push and which one would be the pull? A pull, possibly from rules and regulations that call out the need for meter-based quantification of the energy impacts rather than just relying on deemed averages. And I don't have any examples yet of states that have stepped away from a deemed model. I think that might be a while in coming, but I think that it's very plausible that it could help kind of bridge the gap, focus on more comprehensive DER solutions.
Thanks, Carmen. That sounds about right to me. Steve says, Steve, beyond carbon benefits, how might increasing energy productivity or optimizing energy boost jobs or improve social and economic well-being? I know those, you've already mentioned those as being important. Can you talk a little bit about how energy optimization fits into that?
Yes, I certainly can. One, if you use less energy, then your energy bills are going to be smaller, and that definitely will help economic well-being and economic growth. Also, if you use energy efficiently, we'll have to spend a lot less to upgrade the electric grid, to build new power plants, and that will also provide those direct economic benefits. I'd also point out that there are often substantial benefits in energy efficiency beyond just the dollar and cents savings, whether the home is more comfortable, worker productivity is better because there's less glare and the workers are happier. There have been hundreds of studies documenting these types of effects for many energy efficiency interventions. I don't say it always occurs, but it happens probably more often than not. And then you also mentioned, John, jobs. Energy efficiency tends to be fairly labor intensive, and it's hard to offshore, installing insulation or, doing a custom audit or engineering study. So as you spend on energy efficiency instead of spending, say, on power or energy production, usually there's a lot more jobs generated, say, per $1 million spent than from traditional sources. So that can really help benefit the economy. Currently, the U.S., there's over 2 million energy efficiency jobs, much more, for example, than coal or even, I believe, than oil and gas.
I'm just going to add to that, Steve. I'm sure it only slipped your mind because I know ACEEE has also done research on the public health benefits of energy efficiency that go beyond just addressing climate change and get to more immediate public health impacts.
Yep. Thank you.
Yeah. So this one more question for you, Sue. Should we be concerned about the impact of electrifying buildings on winter peaks, especially, and the infrastructure that will be necessary to keep the grid reliable during winter peaks? Is that going to blow up costs?
Well, it could. It is a real concern as we bring more electric load to our grid. It will add to the peak because on the coldest winter days, we will need more heating, and that's when we generally are asking for more electricity at that time. It doesn't have to be a problem if we follow the guidance to make our homes and buildings thermally efficient, so we reduce the energy requirements at peak. That's first and foremost, is thermal efficiency. Secondly, we need to make buildings flexible to be able to respond to requests to reduce load at times of peak. Again, smart controls, all of that. But by having a thermally efficient building, it's possible to go without a call for heat for an hour or a call for cooling if it's a cooling load without much loss of comfort. And so by having our buildings thermally efficient and having the ability to respond to grid signals, we can reduce the peak impact. But it is something we need to know more about, and we need to invest in both the grid and our buildings to be able to enable that.
Thanks, Sue. We still have some questions to answer, so we're going to go into overtime after the top of the hour here. But I'm sure some people have other things on their calendar. So I want to wrap things up and recap some of what I view as key takeaways here. The first one, theoretically, I think we can get most of the way toward a decarbonized economy with existing renewable energy and energy storage technologies. Some of the technologies are already cost competitive, and really they're all increasingly so with each passing year. But to make decarbonization as affordable as possible, while maintaining high standards for reliability, I think we also need to optimize our use of electricity, and that means making our consumption as efficient and as flexible as possible in order to take maximum advantage of variable renewable energy. Traditional approaches to efficiency have been hugely successful for consumers and our economy historically, and they still are today. But to reach their full potential, I do think, as Steve noted, our efficiency programs and policies need to evolve and adapt. Buildings can and should be a focal point of our efforts and of our policies, not only to reduce their consumption of energy, but also for capturing those potential economic and environmental benefits of flexibility. And lastly, I think it's really crucial that we recognize the time varying and location varying value of energy efficiency, so that we can treat it comparably to other energy resources, and so that we can target more of our programs and procurement efforts on the efficiency measures that bring the most value. So for your convenience, I've included links here to the special issue of the Electricity Journal and to the websites of RAP, ACEEE, NEEP, and Recurve. As a final reminder, if you go to the blog I wrote about the special issue, you will find embedded in the text links to each article that allows you to download it for free for today only. And after today, you're going to need a subscription to Electricity Journal to read the articles. So that's it. Thank you all for joining us today. As always, we welcome your feedback and your questions. For those who are interested, Sue, Steve, Carmen, and I are going to stay on the line for another half hour to keep answering additional questions. For the rest of you, goodbye and have a great day. All right. We do have remaining questions, and I think I'm going to start with Carmen. I think we've just had one from Sue. Let's see, Carmen, I know I had a question teed up for you here. Okay, so do you see, are there smart meters or other tools that are going to enable a utility to directly manage customer appliances in addition to just measuring the usage or procuring energy efficiency through incentive programs?
So I have heard quite a bit about that. I mean, and I think that there are technologies that are going to enable behind the meter management. I think it begs the question, though, of how far behind the meter does the utility have the quote unquote right to go? And I know that might not be very popular with some utility entities that really use efficiency and strategies like this to connect with their customers. But I think that the primary responsibility is to have the transactions of changes in consumption and usage really happening at the intersect between the customer's building and the utility. And that really happens at the meter that is determining their bills and is kind of monitoring the flow in and out of that unit. I think there's another model wherein enabled devices, grid-enabled devices, and other grid optimized buildings, in fact, can really help feed that opportunity to settle a transaction at the meter. But I guess I envision that as happening more through third-party implementers and aggregators that will be able to be delivering services to customers in a more holistic manner as they need to manage their buildings, rather than one-offs for lots of different technologies that will be responding in different ways. So I don't think it's an either or, I think it's an and, but it's not clear to me yet, how that's going to shake out. And I think it does beg some questions of optimization and how and where the market interventions and market signals should be coming from to kind of enable those interventions efficiently.
Thanks. Steve Nadel, I'm going to put you on the hot seat, even though I promised you I wouldn't. All right. So this one gets right to it. Should we stop providing rebates for new gas heating systems despite improvements in efficiency and just incentivize heat pumps? Or is there a time when we should make that transition? Or will there be a time, yeah.
Okay, I don't think we should generally make that decision now. And I say generally because I don't know every local market. but there's still a lot of sales of non-condensing furnaces. And I've heard from a number of people big concerns that if they stop giving rebates for the higher efficiency condensing furnaces, more sales will just go to the non-condensing, and relatively few sales might go to heat pumps at this point. So I would say generally, yes, we should continue to provide rebates for the highest efficiency gas equipment, but we perhaps, it becomes for the 97% efficient and certainly not the 90%. Again, local markets will differ. But at some point, as we can get the heat pump market stronger so that it's a viable option for many homeowners and many contractors, then yes, we can consider phasing them out. That, again, will vary from local market to local market. The other thing I would say is it's vitally important for the gas utilities to continue to weatherize gas-heated homes. They maybe have gas heat for the next 10, 20 years, and particularly with more frequent polar vortexes, they're going to want to reduce their peak loads. And then if at some point they convert to heat pumps, again, we want to have them very well weatherized so that we don't suddenly get major peak problems on those very cold winter days. So for the time being, yes, refine the gas programs, I'd say, and other people, Sue, for example, may have some opinions on this, but don't do away with them.
Okay. Sue, I don't know if you've looked at the role of microgrids connecting multiple buildings. If you have not, I'm happy to toss a different question in your direction, but we've got several questions here about the role of microgrids in decarbonization and improving efficiency. Or actually, I think it's more about the optimization and the flexibility that they can provide.
Yeah. I can say a couple of things. It's not my area of deep expertise, but certainly have been following that development, and there's certainly microgrids evolving in a range of places. There's a microgrid that serves a campus, an overall set of buildings, and there's microgrids that serve neighborhoods and larger populations. They're both evolving. I think one of the questions we need to ask ourselves is, what infrastructure do we want for the future to serve our electrification of our heating and our buildings? And we know it needs to be a flexible, smart grid. So we need to make an investment in our grid to be flexible and smart, and there's some upgrades needed otherwise. There's technology today that allows the utility-owned grid to actually, with a fairly in a small area, for example, to close off that area due to some sort of local outage to contain that outage. And so it's a smart grid that can be self-healing, they call it, that serves almost like a microgrid. It makes an area, keeps an area in power despite something happening in a different area. And so that provides the flexibility. And so we need the ability for the grid. So it's almost like a lot of series of microgrids. So there's a value in that. Can we afford both a lot of small microgrids and a side-by-side big grid? I mean, I think that's a very important economic question that we have to answer. Or can we evolve our grid, our larger grid, to act like a microgrid, responsive to renewables as well as to load? So I think that's a journey we need to figure out what is most economic, what makes it accessible to most people. So that's more questions than answering it, but I think that's the framing we need.
Carmen, I'm wondering if you want to add to that. I realize this isn't the subject of the article you wrote for Electricity Journal, but living in California and having worked with utilities for as long as you have, what do you see as the role of microgrids? I know it's a pretty, I don't even want to say it, hot topic in California?
Yeah, I think I would endorse what Sue just said. I think time will tell where we can optimize. Like I like your comment about, can we afford to have a, investing in microgrids alongside the big grid. I think it's also abundantly apparent that the current grid that we have designed and implemented roughly 100 years ago needs some help and needs some investment in infrastructure. So now it's a convergence of all these different things at the same time is one of the biggest challenges and opportunities kind of our generation. So from that perspective, I don't have a good answer. I think that there have been good examples of how microgrids can contribute to really impacted areas. But I think another thing that we haven't really talked about is how localized procurements can also be optimizing around a wider suite of energy resources that could be available and appropriate for those localized adaptations. And that might be how microgrids kind of live symbiotically, as it were, with the bigger grid through more concentration of the local value of different types of energy resources that are available at different locations, and how they tie in with the building resources that are there and the opportunities to manage those resources, buildings as batteries, as Sue had pointed out, and all the other technologies that could be brought to bear. I think it also speaks to the prioritization questions that are at hand. Out here, of course, rebuilding after intense fires opens up an opportunity to improve efficiency, build it like you want it, but also, you didn't get to plan necessarily where those fires were going to create that opportunity. So I think we just really need to have a wide swath of options that will be launched simultaneously, and then tie them back to what they're delivering and how they're affecting the grid through data infrastructure, so we can really understand how the grid is interacting with customers and create a more coherent bridge, I think.
Yeah, so I think we all agree that that energy optimization is crucial to keeping the grid reliable as we decarbonize. But it doesn't mean that we stop or perhaps even reduce the investments, and certainly not the attention that we pay towards all of the traditional measures that promote reliability. It's very likely that we will have to do both, and lots of both, especially as the existing grid ages. So let's see, I think I'm going to go a little bit more free form here, instead of assuming who's the best person to answer these questions. Let's talk about consumer protection. So I think as we electrify end uses and turn fossil fueled uses, including vehicles, more towards electric fuels, people are going to become more reliant and dependent on electricity. And are there things you think we need to do to enhance consumer protections against the things we've struggled with basically since Edison's time? Troubles with payment, affordability, disconnection. I think the ramifications of disconnecting a customer dramatically increase if all of their energy uses are met through electricity. And anyone have any thoughts about what we ought to be doing there?
This is Sue. I want to just chime in here. I think it's a really important question to bring up. And I'm just going to say that we have the same problem today about energy affordability and disconnections, and access to electricity. So the reality is people use electricity to heat their homes if they're using a gas or propane boiler or furnace, right? You need the electricity to run it. If people are having a hard time affording their energy bills, their propane, their oil, their electricity, we have that affordability problem today already. But that said, we do need protections for consumers. In some states, there is during cold weather a prohibition on disconnecting customers until the weather gets warmer, so nobody's freezing. That's certainly not uncommon here in the Northeast region. And I know in some parts of the Midwest, it's the same thing.
Yeah.
So it is an issue. We do need policies to protect consumers. Another thing that needs protection is going to be data and information. So to manage our smart houses and buildings and grid, there'll be a lot of data flows. And who gets that data, who has access to it, for what purposes, is another area where we need to make sure that consumers are protected. So build this, electric disconnects, we need to make sure people are protected. Energy data being shared or customer information being shared that could compromise anybody. So there are definitely policies needed in this electrification future. Perhaps, Steve, you have some additional ideas on that.
Oh, I think you've covered it pretty well, and happy to move on to the additional questions.
All right, here's another free-form question. Maybe Steve will like this one. So we've talked a bit about the time varying and location varying value of energy efficiency. How should we use that when we're doing long-term program planning or long-term resource planning, especially, and increasingly also distribution system planning? Anyone have some thoughts there?
Yes, this is Steve, and I can weigh in. Certainly, as we are doing distribution planning, we're going to have to think about the time that the power is used. To oversimplify, in the U.S., different circuits typically fall into three categories. They are summer afternoon peaking. These are ones that tend to be dominated by commercial cooling loads. They are summer evening peaking, which means that as people get home from work, that causes and cool down their houses. That's a major load, and certainly as people get home and plug in their EVs, that one may well increase unless we do something to manage that. And then there are the early morning winter peaks. So you really need to think about what the loads are on a given circuit and design both the grid as well as the programs that you're going to use to affect that. Given that there are different peak periods, and peak periods are evolving. Quite a few utilities are finding their summer peaks are moving later in the day, that as we do more efficiency in the commercial buildings and more efficient lighting. Also, as we have solar photovoltaics, their summer peaks are moving later in the day, and some utilities, as heat pumps increase, are discovering that they're going to get winter peaks, particularly on these very cold polar vortexes and things like that. So we have to keep those in account. I also think ultimately we're going to be generally moving to some type of time of use pricing, maybe with an opt-out for those who'd be adversely affected. But as you're doing planning and as you're pricing things, you need to recognize that electricity, as Carmen pointed out, has different values at different times of day and different seasons.
Mm-hmm. Yeah,
Carmen, you have anything to add there?
Yeah, I would just augment that this really ties into this world that we live in now, wherein we can basically meter everything. And by that, I mean, you can have a view of all your customers' current usage and their historic trends and do interesting segmentation, et cetera, with fairly, just our computing capacity has expanded so much in the last, 10 even years. So I think we need to think of that as a resource and how we feed it into our planning mechanisms with adjustments for what the future is going to look like. And there's lots of companies and interesting work that's going on that front right now. And then creating actuarial feedback loops that help us, that is a good tradition from the energy efficiency world, wherein investments in research and analytics to understand what was working and what wasn't. Keep using those sorts of feedback loops, but use them in such a way that they're tied back to the changes in consumption, and make them accessible to planners. I think that's also going to help some of these siloed programs really tie into grid system planning and provide this sorts of intelligence and info that's going to be needed to support finance and investments that will be perceived in those entities as being reliable and trustworthy and demonstrable at the meter.
Well, I might lose my union card for this, but I'm going to step out of the moderator role and add a couple more thoughts to this question about long-term planning. One is that I think the uncertainties about how many loads will electrify and how quickly we will increase our use of electric vehicles argues really strongly for scenario analyses. I think it would be wise to include high electrification scenarios in all types of utility long-term plans, whether at the distribution level or at the bulk power level. And then the second point I wanted to add was that that time value really stresses the need to do to put as much granularity as possible into the resource modeling and the power quality modeling as you can afford to do and as the models can accommodate. With that, I'll step back into
John,
my
this is Sue. I'll just add one more thing to that. In looking at the efficiency and the time value of efficiency and how to use that in planning, the conundrum is that buildings are also the placement of distributed generation. We have lots of PV. We also have batteries going in, not just EVs, but also putting in batteries as a backup for power outages. And so buildings begin to have a profile that's complex. It's not just about what the lighting would do or what the heating would do, and so I agree with everything you said about a scenario analysis and high electrification, but we need to look at it in the context of also other demand side resources, whether they're generation or storage, that are being added to buildings, commercial and residential now at scale. So it's pretty complex, and I agree with you that we need some real thought about that and understanding what the value is at different times.
So I can already tell we're not going to get through all of the questions today, and I apologize to anyone whose question we don't answer, but we're going to go right till the half-hour mark. And I'm going to combine a few things here. We have a couple of questions that relate to rate design, retail rate design. And I think this, again, I'll field it to whoever has something they want to say about rate structures that will be most effective at promoting efficiency and strategic electrification, or what I might call energy optimization. What do you think those rate designs are, and how important are they? Who wants to take that one?
This is Sue. I can start.
Go ahead, Sue. Go ahead.
Rate designs are really important going forward. We do need time of use pricing. It does exist in some states now, not in all, but it is very difficult for planners, designers, customers, managers to make choices if they don't have the price information about what the cost or value of cost of energy or the value of efficiency or demand response would be at any one time. So having rate designs be time of use is important. I've also seen the example of, in addition to time of use rates, having incentives that encourage customers to shift their use at peak periods. So time of use by itself may not be adequate, but also incentives as part of the rate structure. This is a place where I think regulators are fairly behind. They've been slow in many states, I'll say in my region, to adopt these rate structures. I think there's questions about whether customers will really respond to it. And I think this is an area that is lagging generally and needs some real development.
And this is Steve. I'll just add one thing. You talked about rate structures, and those are important, but you also talked about electrification. If we're going to have electrification, we have to pay attention to the relative price difference between fossil fuels, typically natural gas, which is a regulated fuel, and electricity. And do we need to, this is important, do we need to start putting a price on carbon, for example? Because currently, varying from region to region, the economics of installing a heat pump are often not compelling. Yes, you might have life cycle cost savings, but you're often talking simple paybacks in excess of 10 years. So if we want electrification as a policy objective, we need to be thinking about the rate structures and the tax structures that might help that to happen.
Do any of you see either optional or mandatory real-time prices as being important to optimizing energy use?
This is Steve. Certainly there's always the option of optional, maybe for large customers, but the average residential customer or small C&I customer is running their business, running their home, and would probably have difficulty being that responsive to a real-time price. I'd be very reluctant for small customers to start mandating it, as opposed to trying to get it approximately, get in the ballpark, if you will, with some type of time of use rate.
Yeah, I would second that. And I think if it were to go, I think the opportunity there is that if you were to allow other third parties to play in that space and kind of create a buffer for customers and take on some of that risk, then it might be viable. But that introduces other questions of customer protections that probably would need to be considered.
Right. You can do various set and forget type structures, but yes, you have to be protected. You have to know what you're setting.
Right.
Right. I'll take off the moderator hat one more time and share with everyone that a little known piece of news. I'm a customer of a medium-sized municipal electric utility, Fort Collins Utilities in Colorado, and our utility has put residential customers on mandatory time of use rates for more than a year now. And I haven't seen data on the impact it's had, but I would just want to reassure people that thus far, and I'm knocking on wood, there has not been rioting in the streets with residential customers on time of use rates. It's an interesting program, and I think all of us are looking forward to seeing some of the data analysis on the impacts it's having on consumption patterns and total consumption.
Yeah, could I note one other thing? CUB, yeah. The Citizens Utility Board, did a really interesting study just this last year on the potential effects of time of use rates for low-income customers, and basically debunked the myth that they would inherently be damaged by it or harmed by it. So they had access to AMI data to do that analysis, which was really important.
Yeah, if anybody wants to learn more about that study, contact me and I'll point you in the right direction. But I think that's going to have to be the final word on today's webinar. I want to thank our three panelists, thank the audience members for teeing up a whole lot of great questions. I hope it's been a good use of everyone's time. And again, we'll be sending links to the recording and the slides in the coming days. Enjoy the rest of your day and goodbye.